Let's talk some more about binocular disparity. As I mentioned before, is a technique that's very widespread through animals, and it's also a technique that's used in robotics. A good way to try and understand the principle of binocular disparity is to look at this very old-fashioned stereo photograph. It's a pair of photographs of the same scene, but each image has been taken from a slightly different viewpoint. And this corresponds to the viewpoint from our left eye and our right eye. They're separated by about 8 to 10 centimeters. And they give you a very slightly different view of the world. Initial inspection of this stereo photograph indicates that there's not much difference. If we zoom in on a couple of areas here, we see that in the left-hand image there's quite a gap, and there's in fact no gap in the right-hand image. And if we look on the other side of the picture, we look at this bench. It's quite close to the edge of the image in the left picture, and there is a bit of a gap between the edge and the bench in the right-hand image. It's these very subtle differences in the image taken from these two viewpoints that gives us this very vivid three-dimensional perception of the world that's around us. The fundamental principle of stereo disparity is that the image depends on the camera position, and we can demonstrate that pretty easily. If I move my head, if I translate my head from the right through to the left, then everything that's in the world appears to move to the right. But importantly, things that are close to me, like this robot here, appear to move a lot in the image as I do that shift, whereas things that are far away, like the bookcase, appear to move much less. Now, people have been interested in capturing stereo photographs for a very, very long time. This is a lovely picture I found of a commercial stereo film camera from the 1950s. A more modern version of a stereo camera, this is a digital stereo camera of the type that's quite widely used for robotic systems. Let's now try and understand more precisely the difference between the left-hand image and the right-hand image of the same scene. This is a pair of high-resolution digital images of a pile of rocks. I'm going to draw a line from the left-hand edge of the image to a fairly distinctive blotch on one of the rocks. And I'm going to draw the same length line in the right-hand image. The yellow line has gone too far to the right. I in fact need to go back a distance in order to get to this distinctive mark on the rock. Let's pick another distinctive feature at the back of the scene here. So I'm going to draw a yellow line from the left-hand edge to the edge of one of the large blocks at the back. I draw the same line in the right-hand image, and again we see that it's overshot the corresponding point, and I need to go back a distance in order to get to that corresponding point. We notice two important things. First of all, we notice that points in the right-hand image are shifted somewhat to the left, and this shift, this horizontal displacement, is referred to as disparity. We also note that this shift is less for points that are further away from the camera. So here we have a stereo camera and is observing an object, a ball, and that is at a distance z away from the camera. We refer to the baseline of the stereo camera. That's the distance between the centers of the lenses, and f is the focal length of the lens. We assume that both lenses have the same focal length. Now there's a very simple relationship between these quantities, and that is that the disparity is proportional to the focal length and the baseline divided by the distance. So if we know the focal length, we know the baseline, and we know the disparity in the image, then we can estimate Z. This is the fundamental underlying principle of robotic stereo vision, sometimes called computational stereo, and implicitly it's what happens in our own visual system.